So in this problem, we want to find the area of the region that's enclosed by one loop of the curve r equals 4 cosine of 3 theta. So there are two things I want to do here. So number one, I want to do a little bit more practice with curve sketching. So we're going to try and sketch this curve. Number two, we're going to set up the integral. If you want to skip ahead until we set up the integral, be my guest. No offense taken. And find the area. Okay, so in terms of sketching, we have the function r equals 4 cosine of 3 theta. Notice that we have a cosine function. So if we choose positive or negative theta values, we're going to have the same r. So we have a symmetry across the polar axis. What this means is that it's enough for us to sketch for theta in 0 to pi, and then we can just copy our picture across our x-axis. Okay, so we don't really have an x-axis, but flip it across that that polar axis. Okay, so I've drawn the polar axis in blue. All right, so let's get started with this thing. So we are going to start with a sketch of our theta versus r graph on theta equals 0 to pi. Okay, so we have this basic sketch with values at pi over 6, pi over 3, pi over 2, all of the multiples of pi over 6 shown. Let's fill some of these guys in. This is height 4 and this is height -4. Okay, so at angle 0, we're here at 4. At pi over 6, we are down here at 0. At pi over 3, we are at radius -3, so that means we're going to be following this ray across to 4 pi over 3. And so our we're going to be at this point here at 4 pi over 3, which is at angle, so this is the point -1, or -4 rather, pi over 3. All right, at pi over 2, we are back at the center. At 2 pi over 3, we are out here at radius 4. And at 5 pi over 6, we're back at the center. And at pi, we are at radius -4. So we start out on, so we're on this line, and it's negative, so instead of being on the pi side, we're at the 0 side. So we end up back where we started. Okay, so this gives us sort of a picture, but we want a little bit more detail. So let's also consider some other points. So for example, at pi over 12, so I'll put theta here and r over here. At pi over 12, r is equal to 4 cosine of 3 times pi over 12, which is 4 cosine of pi over 4. So we get 4 over the square root of 2. And this is around 2.8 or so. So that goes here. So our curve looks kind of like this. You can see we're going to have rotational symmetry from this cosine of 3 theta. So if we also evaluate at 7 pi over 12, for instance, we're going to see 4 cosine of 21 pi over 12. Okay, so this is 4 cosine of negative 3 pi over 12, or 4 cosine of negative pi over 4. And we simplify down to being just 4 over the square root of 2 also. So this is the same radius. And similarly, if we look at 3 pi over 4, we have 4 cosine of 3 times 3 pi over 4. We get 4 cosine of 9 pi over 4. Which we can simplify down to being 4 cosine of pi over 4. So we're subtracting 2 pi. And so again, we see that same radius. So we've got one here and one here. So we have these petals forming. All right. So we're trying to draw these so that there's only one radius at each angle theta. And if we do the same picture, you can see we should be able to rotate this, that this should have symmetry. We end up actually filling in the rest of the picture. We could either recalculate these values for these remaining 2 points, or we can just reflect across the polar axis. Oops. All right, and so astonishingly, we've done it. We've drawn this beautiful curve. Now let's talk about setting up the integral to find the area. Notice, so we only want to look at one loop, so we're going to be integrating from negative pi over 6 to pi over 6. It doesn't matter which loop we choose, but I think it makes sense to just look at the loop corresponding to these angles. And then we're going to be using our area formula. We'll do this in the next slide. Now that we've sketched this curve, let's find the area of one petal. Remember that we're using the area formula, so the integral from a to b of 1/2 r squared d theta. And our equation for r is 4 cosine of 3 theta. So our area is going to be the integral from negative pi over 6 to pi over 6 of 1/2 times 4 cosine of 3 theta squared d theta. Notice from symmetry we can actually cut this down a little bit. We can instead take twice the integral from 0 to pi over 6 of this integrand, so 1/2 times 16 cosine squared of 3 theta. That's nice. We like that. Okay, this guy simplifies to the integral from 0 to pi over 6. 16 cosine squared of 3 theta. D theta. All right, to simplify, to do this integral, we're going to need our half or double angle formulas. So that says that cosine squared of x is equal to 1 plus cosine of 2x over 2. Here, in our problem, x is equal to 3 theta. So 2x is going to be equal to 6 theta. So we can make our integral, the integral from 0 to pi over 6, 16 times 1 plus cosine of 6 theta divided by 2. All right, we can simplify this guy just a little bit. We get the integral from 0 to pi over 6 of 8 times 1 plus cosine of 6 theta. Okay, now let's integrate this. We get 8 theta plus sine of 6 theta over 6, where this 8 gets multiplied by both terms. And we're integrating between 0 and pi over 6. Okay, so this gives me 8 times pi over 6 plus sine of 6 times pi over 6. Oops, that's going to be 0 over 6. And then the second term is just going to be 0 plus 0, so minus 0. And so we can simplify this down to 8 pi over 6, or 4 pi over 3. And this is our final answer. This is the area of one petal.